Stephanie and Bruce, if you have questions, please stop me or put them in the chat. But I'm going to try to go over everything. I'm going to stop at 11 if we get too long. But I'll try to get even the fluid question if I have time. And if you want to leave, go ahead and bail out of here. It'll be recorded and I'll post it tonight. So first homework is homework 8, 9, and 10, which is most of what we went over on Monday. Work, energy. So this first one is a 25 kilogram box sliding to the left, brought to a halt by a horizontal rope pulling to the right. How much work is done by the tension and how much work is done by gravity? So what we have, if I read that right, is we have a box that's moving this way to the left, and there's a rope with tension trying to pull it back that way to a stop. So the box is 25 kilograms, and if brought to a halt in a distance of D, I'm sorry, these are the things. It's brought to a halt in 55 centimeters by a 16 Newton tension. So we want to know how much work. The definition of work is F dot D. Here, our F and our D are given as 55. Yours are obviously different. Remember to put that in meters. Work has to be in joules, which are Newton meters. And this is 16 newtons, but this is our tension. Now, they're not asking for a negative sign in this, so you can just take the absolute value, but what we would see is that D is this way and T is this way. And therefore, the angle between these is actually 180 degrees, which means that this is FD cosine of the angle, and this would actually be -1. But just take the positive digits point the magnitude. So this is 16 times 0.55. Now, that is 16 times 0.55, 8.8 joules or Newton meters. So a joule is a Newton meter. The work done by gravity. So gravity is going to be our weight forced down, and D is going to be this way. And that angle between them is 90 degrees. So if we look here, the weight times D times cosine of 90, this is 0. And therefore, the weight of gravity will be 0. Hi, Ruben. So we get minus, oh, I guess there is a minus sign. So minus 8.8. So don't use the absolute value. It's minus because it's slowing it down. Remember, another definition of work is the change of kinetic energy, and it stopped. The change of kinetic energy means the work is also delta KE, which is mv final squared minus mv initial squared. And since v final will be 0, the work will be negative. Just make sure you know that. Signs are important. So 0 joules is the work of gravity. And that's because the displacement and the work of gravity are 90 degrees off each other. If they're perpendicular, no work. Basically, that's saying that the gravity doesn't change its kinetic energy at all. Is another one. All right. So in this one, we're going to throw a coin straight down 4 meters per second velocity of a 75-meter high bridge. How much work does gravity do as the coin falls? So the work done by gravity is actually mgh initial minus mgh final. The potential energy of gravity is mgh. The work done by gravity is the negative of the change of potential energy, and the change would be mgh final minus mgh initial. So this is the work done by gravity. That work is going to result in the coin speeding up. mv final squared minus mv initial squared. So it's going to increase the speed. It has to be positive work. We're going to assume that at the ground, H final will be 0 and H initial will be the initial height. So 75 meters. Okay. Right now, we don't need to worry about this initial speed, and we don't need to worry, actually, we do need to worry about the mass. So the mass is 0.0055 kilograms, or 5.5 grams. This will be 0, H final will be 0, so this will be 0.00, and that's my dog being annoying. I don't know what she's doing. And so our work will be 0.0055 times 9.8 times 75 for me. I get 4.04, so 4.0 joules. If I'm going to use 2 sig figs, 4.0 joules. Now, what is the speed as the coin hits the water? And this is very important. So we're going to call this, and I moved this around. Let me get rid of this here. We're going to assume that our energy initial and our energy final are here and here. Our energy initial will equal our energy final by conservation of energy. So mgh initial plus mv initial squared over 2. There's no spring here, so we don't have to worry about spring. We only have to worry about gravity and kinetic energy. We've done this enough times. Since H final is 0, V initial was not 0, however. Let's cancel all the m's, and then we'll multiply through by 2. And what we get is we get that V final squared, so is equal to square root of 2gh initial plus V initial squared. Now this is 2, 9.8, 75 plus, I think it said it was 4. I don't remember. Yeah, 4 meters or meter per second squared for me. And remember, that is not the energy, that's the initial velocity that it had. Coincidentally, for me, they're the same, but for you, they're probably not. Plus 4 times 4 is 16, and square root of this answer, I get 38.5. So I get 39. This will be 39 meters per second. Seems about right, 39 meters per second. It did fall a very long way. So just to recap, the work done by gravity is the change of potential energy of gravity. That's just mgh initial minus mgh final. And we're assuming that h final is 0 in this problem. And then if we use conservation of energy, we can solve this for V final. Just remember that you do have a V initial here. At least you should. Okay, so just make sure you know how to do this. It's not too bad, I hope. All right. Now these are about the dot product. So we have 3 pairs of vectors, and evaluate the dot product of the vectors A and B. Now, the dot product, this was just to remind you that when you have A dot B or B dot A, you always put them tail to tail, figure out the angle between them, and then the dot product is A, B, cosine of the angle, AB. So if we look at this first one, for me anyway, it's easy. They're already tail to tail, A and B. So that would be 3 times 4 times cosine of 130. And always take the angle less than 180. We wouldn't go that way. So I get 12 cosine of 130. And that's negative 7.7. Okay. Now for D and C, the angle between them is going to be the angle between D and C, if we put them tail to tail, So if we look at this and they're tail to tail, the angle between them is 180 degrees. And cosine of 180 is -1. So when you do this dot product, D and C, it's 5 times 4 times cosine of 180, so -20. And then finally, E and F, we need to move them to tail. So if we do E and F, we look here, we actually need to move this over and get the angle here. And that angle, this angle was 130, the whole angle is 180, so this is 50 degrees. So it's E times F, 50 cosine of 50 degrees, or 20 cosine of 50 is 12.9. 13. Although technically it would only be 1 sig fig, but okay. I get 12.9. So just make sure you understand that when we dot the work, you have to dot the force and the distance. So pretend E and F are force and distance, D and C are force and distance, A and B are force and distance. This will be negative because the part of A that's opposite of B is anti-parallel. They're anti-parallel. They're in the same direction. So that's why the last one is positive and the first two were negative. But just make sure you understand how to do that. All right. So now we're going to talk about springs. And a horizontal spring has a spring constant of 750. An athlete presses against a free end and compresses it 7 centimeters. What is the force? So K is 750. And what was D? Or let's call it X. Sorry, don't use D. We'll call it X. So X is going to be 7 centimeters, but we need it in meters always. Now the force of a spring, the restoring force is -kx. Okay, but he's actually pushing on it, so we're going to take a positive value here. So all we have is 750 times 0.07. That's easy enough. 750 times 0.07. 52.5 newtons. The units here are Newton meters. Units here are meters. We get newtons. So 53 newtons. Okay. I just want you to know that. So when your hand is pushing on the spring, okay, and it pushes in from its equilibrium where X is 0, it pushes into X is -0.07, and that there's a K. The force from the spring pushing back is -kx, but because X is negative, the force is positive. That's all. So this one's not bad. All right. Okay. So now it extends outward from the wall. A 1.5 kilogram box slides, hits the end and compresses it. And then the spring expands and shoots it out, back out. How fast was the box going when it hit? So whenever we have energy of a spring, what we have here is that we have before the spring's end is at 0 and the box is sliding this way. And then we have this one moment where it completely compresses some amount. So X final, and V is 0 for the box, and it's compressed. So our energy when we have a spring, we're going to ignore mgh because the h doesn't change. This would be mv squared over 2 plus spring potential energy, kx squared over 2. We always have to choose a 0 point for our spring. But if we set this is 1 and this is 2, or this is initial and final, I have that the energy initial 1 is equal to the energy final. So I have mv1 squared over 2 plus kx1 squared over 2 is equal to mv2 squared over 2 plus k over 2x2 squared. Initially, spring is not compressed at all, so it's 0. And when it stops, the spring is compressed. So what we have is we have mv1 squared over 2 and k over 2x squared, or x2 squared. Now we were told that k was 85 and it would compress 6.5 centimeters, 85, and x was 0.065 meters, 6.5 centimeters. And the mass of the box is 1.5. We want to know what is v. So mv1 squared over 2 is equal to k over 2x squared. Now the 2's cancel. We get that v1 is k over m x squared, and then take the square root. So I have 85 over 1.5 times 0.065 squared. Now, 85 over 1.5 times 0.065 times 0.065, and then take the square root. Don't forget to take the square root. I get 0.49 meters per second. 0.49. Okay. They just pulled the x out, but if you left it inside the square root. Okay. So when we have a spring, just like with gravity, where we do mgh mv squared, mgh mv squared. For a spring, we do mv squared over 2 plus kx squared over 2 is equal to mv squared over 2 plus kx squared over 2, assuming there's no change of height at all. So it's not too bad. All right. We want to know, on this, a baggage handler throws a suitcase, it rolls across the floor at an initial speed of 1.2 and slides to a stop after 1.6 meters. So let me draw this. It starts here, okay, and it's got a velocity of 1.2 meters per second, and it has a mass of 15 kilograms. And then it travels a distance of 1.6 meters, and it comes to rest. Now, the initial energy and the final energy are the following. mgh initial plus mv initial squared over 2 is equal to mgh final plus mv final squared over 2. However, there is friction. And the work of friction is always mu n. For a flat object, n is up, weight is down, so n is mg. Therefore, sorry, times d, this is our d, mu n d. We can either subtract it from the initial or add it to the final. I'm going to add it to the final. Mu mg d. That is the work of friction. Now our h's go away because there's no change of height. Our v final goes away because there is no final velocity. So essentially it has zero energy at the end. All the kinetic energy it started with becomes friction. Okay, so what we have is mv initial squared over 2 is mu mgd. And we want to find the coefficient, so we want mu. So mu is mv naught squared over mgd and a 2. The m's cancel. I get v naught squared over 2gd, 1.2 over 2, 9.8, 1.6. I think we did one like this on the practice exam, but I'm not totally sure. Divided by 2 times 9.8 times 1.6. I get 0.046. And that unit has no unit. It's mu. The coefficient of friction is mu. So make sure you know how to do this one. Make sure this one makes sense to you, both mathematically and conceptually. The initial kinetic energy was all lost to friction. So the initial kinetic energy has to equal the energy lost to friction. Otherwise, it would still be rolled. Okay. right. Let me make sure I did that right. 0.046. All righty. We're about halfway done with this. I'm going to try to go through all of them. I am recording. If you have to leave, if you have a question, feel free to, as always, throw it in the chat. For everyone here that I forgot to mention at the beginning, I have 1 page left to grade on 30 tests. So I have about an hour of grading left on your tests. They're weirdly split. About a third of you did bad, about a third of you did, and about a third of you did well. But we're going to talk tomorrow about what we want to do, and I'll have your grades for you, and I'll pass your test back tomorrow. Definitely. So we'll talk about it. But yeah, so I think you probably know how well you did. But I'll also figure out what the average is, and we'll have a couple different options, and we'll just talk about it tomorrow. So just know I'll be handing back your tests and talking to you guys about it tomorrow. And then we'll have our test for it. All right. How much work does an elevator motor do to lift a 1,100 kilogram elevator a height of 110 meters? Now, the work done by the elevator or motor on the elevator, it has to lift it from MGH initial to MGH final. Now, it is lifting it against MG. So it's basically lifting it at delta H against MG, which means it has to do a work of MG delta H. Might seem like we would have to do energy or something else, but this is really just the concept of work. 1,100 times 9.8, that's our MG, times our height change, which is 110 meters, is 1.2 times 10 to the 6, which is what they got. Now, you may be saying, well, wait, isn't work F dot D? And yes, but that's the work done by gravity, okay? We do the negative work. The elevator does the negative work. So the work of the elevator is the negative of the work of gravity. So it's H final minus H initial. It's all, it's work has weird signs, okay? Now, how much power, if it does this work at a constant speed in 59 seconds? Now, power is the change of energy over the change of time, but the change of energy is the work. So power is work over time. Another definition of power is ddt of the work, remember, is force times distance. But if we move the force here, the change of, let's call this x, the change of x with t, if it's an average force times a constant velocity, you also have the power. We don't have that here. Here, we're just going to do this. So take your work, your 1.2 times 10 to the 6 joules over whatever it was, 59 seconds. Don't round it. Use your original answer. I get 2,0100 watts. So W, but it's for watts. 2,100. They're saying just 20,000, but I got 2.01 times 10 to the 4th watts. That is watts. Joules per second. Watts. All right. So a process occurs in which the potential energy increases while the environment does work on the system. Does the system's kinetic energy increase, decrease, or stay the same? So one thing that we need to remember is that work is the change of kinetic energy. And that is equal to the negative change in potential energy of a spring or gravity. If this goes up, the kinetic energy goes down. Think about throwing a ball up. As the ball rises, its gravitational potential energy increases as it slows down. It loses kinetic energy. However, as it falls, its potential energy decreases while its kinetic energy increases. They have an inverse relationship. So does it increase, decrease, or stay the same? Okay. I don't know why this is saying that. Oh, I guess what they're saying here is that it's unknown because we don't know how much work is being put in. So we could be putting enough work in to increase its potential energy and its kinetic energy, or enough to keep it the same. So that's unknown. But what I really wanted you to think about is the relationship between potential energy and kinetic energy. That's a really bad question. I thought that question was different when I read it. Sorry, but the answer is unknown. We don't know because we're actually putting energy in. It could potentially be increasing both of them. All right. This is a jet lands on an aircraft carrier and the tail hook slows it down. This is a spring problem. And that spring constant is very big. So what we have here is we essentially have a jet that is flying at some initial, it has a some initial velocity, and it grabs a spring, and the spring stretches from equilibrium some distance x and stops the plane. If you haven't ever seen a plane land on an aircraft carrier, they land with basically big cables. So the energy here is mv squared over 2, and just like before, okay, x squared over 2 because there's no more kinetic energy when it's stretched. Now they told us that x was 33 meters to stop the plane. So here, x is 33 meters, and k is 6.5 times 10 to the 4th Newton meters, and the mass was 1.7 times 10 to the 4th. 1.7 times 10 to the 4th kilograms. These things are equal. We want the velocity of the plane. Again, the two cancel, and the velocity is k m over x squared. Now, one nice thing is these are both 10 to the 4th. So this is 6.5 times 10 to the 4th over 1.7. The 10 to the 4th cancel. 33 squared. All right, 6.5 divided by 1.7 times 33 times 33. Square root of that answer is 64.5, or 65 meters per second. 65 meters per second. So this is essentially the exact same problem that you had before, just another spring problem. It's another way of seeing a spring problem. You might not think of a cable as a spring, but that's what it is. All right, next up, this is a potential energy diagram. The thing about this is, when it's at the top, it is all potential energy. When it's at the bottom, it is all kinetic energy. So the most energy it can have is 5 joules. Some of that might be potential, some might be kinetic. At B, it will have 5 joules of kinetic and 0 of potential. Here it will have 5 joules of potential, 0 of kinetic. Here it will have 2 of potential and 3 of kinetic. Okay, so the minimum speed does a particle need at point A to reach point B? It has to have enough energy to get over this hill. Okay, so it better have, at this point, it has 2 joules of potential energy, and it needs to have 3 joules of kinetic energy. So when you read this, when you read a potential energy diagram, essentially, and it's in joules. So at any point here at the top point, all potential, or U is potential energy. And at the bottom, all kinetic energy. Here it has 2 joules, but we need at least 5 joules of total energy to get up that hill. So it needs to have at least 3 joules of kinetic energy here to get up to the top. Now, 3 joules of kinetic energy is equal to mv squared over 2. And they asked us what is v. So v is the square root of multiplied by 2 over m. 2 over m is just units. So I get 6 over m, take the square root. And 6 over m, what was m? 100 grams? 0.1 kilograms. So 6 divided by 0.1 is 60. Square root of 60 is 7.75. 7.75 meters per second. Or 7.7. Okay. I just want you to be able to read this. What minimum speed does it need at point B to reach point A? Now at B, it needs to have 5 joules of kinetic energy because it has to have enough energy to get up that hill. And it's all it has at B is kinetic. So 5 joules is mv squared over 2. And this is B is 2 times 5 over m, which is 2 times 5 over 0.1. That's 10 divided by 0.1 is 110 meters per second. Okay. So just make sure you kind of understand what's going on. They won't be on the test, but those of you that are biologists or chemists will eventually start using, if you haven't already, start using potential energy diagrams to understand reaction rates and biological processes. Basically, if at B, it doesn't have 5 joules of kinetic energy, it won't go all the way up. It'll get turned and head back. If at A, it doesn't have 3 joules, it has, say, 2 joules, it will get up to 4, and then it would turn and go back the other way. So a potential energy diagram just kind of shows you what can happen in a graphical way, which makes it easier for us to understand. All right. Now on, hello? I don't think you need it. All right, so a spring has a student, gets launched, it's frictionless until we hit the incline, then we have to deal with the incline. So first of all, what is the speed after we lose touch with the spring? Now in this problem, we have basically, we're going to have 4 different points, okay? When the student's first, and I'm going to use a block for the student, then when the students cleared the spring, so the spring will be compressed some x, there's going to be b, there's going to be b at the bottom, and there's going to be some point here where v is equal to 0, I think. We'll read that when we get there. But let's call this A and call this B. Now the energy at A and the energy at B and the energy at C, we'll deal with D when we get there. All we have to do is write the following. There's no friction until we get over here, so we don't need to worry about this part yet. mgha plus mva squared over 2, mghb plus mvb squared over 2, mghc plus mvc squared over 2. And there's actually spring energy here. I don't want to write a ton of, I don't want to write them all the time, but there is spring energy here. There is no spring energy at B or C. So we can write them and then just cross them out. Now, in order to find the speed right when they lose contact, we want to compare the A to EB, set them equal to each other. The heights are the same. So what we have is we have mba squared over 2 plus kxa squared over 2 is equal to mvb squared over 2. However, this is 0 as well. So really we just have this. Cancel the 2, divide through by m, and we get that bb is the square root of k mxa squared. Okay, so k, shown here, k is given Okay, is given in the picture. My brain is not working. 80,000 divided by the mass of the student, which is 100 kilograms. And then we're going to multiply that by how much we compressed in meters, 0.55. And we're going to square that. And then take the square root of the entire thing, and I get 15.6. I actually get 15.5563. We're going to keep that for a second, but our answer is 16 when we round it. Now, how far up the incline does the student go? We don't need to worry about C so much, but we do have to be super, super careful. Notice that the bottom here is 10 meters, and we want to measure how far up. I'm assuming they want to know how far along the incline, okay? All right, so we have to think really hard about this. Everything that we've learned. We know that starting here, and then we're going to go up to some point D, and we're going to start at some point B. This will be 0. We're going to measure from here. H will be 0. So we have mGHB plus mBB squared over 2. That is the energy at B. And then we need the energy at D. Now the energy at D is going to be mGHD plus mBD squared over 2 plus there's friction. The work of friction is mu n times the height at D. But the height at D, okay, is equal to x is our hypotenuse times sine of the angle. So HD is going to be equal to how far we went up the incline times sine of the angle. N, since we're on an incline, remember N is mg cos theta. So this work of friction is going to be mu mg cos theta times height d x sine theta. And we want to solve this for x, but energy at B is equal to the energy at D plus the work of friction. So mu mg cos x sine theta. This is our D, this is our N. This whole thing is the work of friction. Now we know it comes to rest, so that goes away. And we also know that this is also x sine theta. So let's rewrite this. mGHB plus mBB squared over 2 is equal to mg plus mu mg cos theta times x sine theta. Okay, they're both times x sine theta. We need to solve this for x. So x is equal to mg hb plus mvb squared over 2 divided by mg sine theta plus mu mg cos theta sine theta. I should have pulled the, I'm going to leave the sine thetas in. We're solving for x, which is how far up the incline we went. The m's go away, but who cares? We can leave them in there. I'm going to try to make this so that I can see what I'm doing. So mGHB, HB is 10. That is 100 times 9.8 times 10 plus m, which is 100 times 0.5 or divide by 2 times, remember BB was 15.5563 times 15.5563. So what I've done is I've computed this, and that's 21899. So this first part, x is equal to 21899.123. And then this part is, sine is 30. So 100 times 9.8 sine of 30 plus the mu was 0.18 times 100 times 9.8 times cosine of 30 times sine of 30. And this is 660.389. 660.389. If I divide 21899. 0.923 by my answer, I get 33.1, so 33 meters. They got something slightly different. This is my 10, 9.8, or 100 times 9.8 times 10. Oh, I think they used 16. I didn't use 16, I didn't round it up. But if I had rounded it up, I would have gotten 34. Over mg sine of the angle, they're using radians. I use 30 times mu mg mu cosine of 30. What happened to my sine? They're like missing a sign over there. But I think that's a typo on their end. But they got 34. So maybe that's why. Maybe they missed that sign. Yeah, who knows? So yeah, it's this is about as hard as it gets. Okay. And that's just because you have to remember that when it goes up the incline, x h is x sine of theta, and the energy when it got to the top was mgh plus mu mg cos times x. Oh, I'm dumb. I messed that up. So they didn't mess that up. So what we have is we have mgx sine theta plus mu mg cos theta x. I put a sign here and it's not sine, it's x. And that was equal to the initial energy of mghb plus mbb squared over 2, which is equal to ED, and ED is equal to mg x sine theta, which is mgh, plus the work of friction, and the work of friction is mu mg cos x, and you get 34. So yeah, x is equal to mghb plus mbb squared over 2 divided by mg sine theta plus mu mg cos theta. Alrighty. Now, so it's your birthday, you're going to make a bungee jump. You stand on a bridge 110 meters above and attach a 25-meter long bungee cord. Bungee cord, for practical purposes, is just a long spring with a spring constant of 48, and you have a mass of 70. After a long hesitation, you step off. I don't know why they tell such crazy stories. How far are you above the water when the cord reaches its maximum elongation? Now we need to think about this carefully. We are starting 110 meters above, okay? Above the water. And the thing doesn't start to elongate until we're at 25 meters. So we can think of this as a spring, right? And this is where x is equal to 0. So when it said x is equal to 0, it's at 25 meters below the bridge. Now, we need to figure out what the maximum elongation is using energy, okay? So I'm going to set my height 0 here. Trust me on this. And then this thing's going to stretch to some maximum distance, and I'm going to have some h final. And I want to find that h final. So the energy here and the energy here are mgh, and I'm assuming that mv squared here is 0 plus kx squared over 2. But since h and x are 0 here, and x is also equal to h final here, and this is my, I'm starting from rest, and then my final is mgh plus mv final squared over 2 plus kx final squared over 2. And now, setting these two things equal to each other, okay, I get that 0 is mgh final plus mv final squared over 2 plus kx final, but x final is also h final squared over 2, okay? And I want to figure out what is h final. Now, first of all, I can get rid of my m's by dividing through everything by m. And I get k over m. Now, if I remember negative b plus or minus b squared minus 4ac over 2a, my a is the one attached to the squared, so it's k over 2m. My b is the one attached to the single, so that is g. So this is a, and this is g, and c is point b final squared over 2. Oh, I'm sorry, I don't need to do all this. I forgot. There is no b final because we come to rest. So let me put this all back. This is 0, so I get mg h final plus k x final, but that's actually h final.
Professor,
Yes.
so we cross out v initial because so it starts at rest and it ends at rest. Is that how we're looking at it?
Yeah. So we're bungee jumping, and we're assuming that when you stretch it all the way, you stop before you start. You get pulled back up.
Okay. Yeah.
Okay. So if I move this over, I get that mgh final with a negative sign is equal to k h final squared over 2 divided through by h final, and I get negative mg is k over 2 h final, or h final is negative 2 mg over k. And that's good because it should be negative. This is 0, so h final should be some negative number. 2 mg, what was our mass? 70 kilograms. We're going to assume that that's the mass of everything, massless rope. 2 times 70 times 9.8 divided by k, and k is 48. So I get negative 28.6 meters. But being mastering physics, they want to know how far above the water we are, right? How far above the water. So we went down minus 25, and then we went down minus 28.6. So subtract another 25, and I get 110 minus 53.58. I'm at about a height of 56.4 meters. I don't know what they're doing here. Why did they get 40? What did I do wrong? Okay. Let me try that again. Make sure. So they, so 2 mg. What? Oh, they did a bunch of stuff. This is 4ac. No, it's 4b. A must be 1. And B and C are the same. I don't know what they did there. So let me do this again. So maybe I messed something up. We elongated 25 meters. So we started at a height of 110 meters. This is where H initial is 0 and X initial is 0. And then we stretch down to H final, where X final is H final. And our energy there, if we start off at 0, is mg H final plus K to the half H final squared. Divide through by H final. And I get that H final is negative 2 mg over K. Did I do something wrong there? So that is 2 times 70 times 9.8 divided by 48. I get 28.6. So they're saying that this should add up to 70, which would mean this would have to be 45, which I'm not seeing. It's so weird. This is the other thing that's bugging me here. This has H minus L in it, and I don't get what they did here. So anyway, yeah. Oh, okay. Right. So this is saying that I have, but if Y initial is 0, oh, yeah, this is 0. So I let Y1 be 0. I don't get what they're saying here. But anyway, here's your answer. The way they did it. They did do a quadratic here. And they're saying that the initial energy is mgy2, 1/2 ky2 minus y0 squared. However, I maintain that you could say that y2 is 0. And furthermore, that y1 and y1 are equal. And in that point, you get a different answer than what they got. Now they're saying that y0 is y1 minus L. Right, but y0 they're saying is at 85. But what if 85 were 0? And that is the point. Also note that U1, since the chord's not stretched, right, at y0, we're calling that x is 0. So I think they messed this one up, unless I'm really dumb. And if I say that y2 is, yeah, it's weird. I don't know what they did there, because that would eliminate this guy. And this guy. Am I just missing the initial change? Oh, I think I am. I'm sorry. I know what I'm missing. I know what I'm doing wrong. Sorry, brain's not working completely well. Okay, so first of all, what we have is we have that we have mg. So the energy at A should be equal to the energy at B, should be equal to the energy at C, and we're going to assume that the rope is stretched at all. So this is mg times HA, and then this is mg HB and kxb squared over 2, and then finally mg HC plus kxc squared over 2. Got it. Okay. I'm going to assume HB is 0. HA is 110 meters, the very top. HB, and that's equal to XB, and then HC is equal to XC. And so what I get is I get MGHA is equal to MGHC plus, I forgot the initial change. However, instead of doing what they did, okay, what I could have done is I could have, no, I guess I couldn't have. So yeah, this becomes 0 is k HC squared over 2 plus MGHC minus MGHA. And this, if I multiply through by M, I can get rid of all these. And what I get is the following. A is K over 2M, and K was 48, M was 110, so 48 over 220, 2.18. G is 9.8, and that is my B, and C is negative 9.8. So what I get is negative 9.8 plus or minus 9.8 squared minus 4 times 0.218 times negative 9.8 over oh, this was times 110. So 9.8 times 110, 1078. Negative 1078. And over 2 times 0.21. That's negative b plus or minus b squared minus 4ac over 2a quadratic. So 9.8 times 9.8 minus a minus, so plus 4 times 0.218 times 1078. Square root of that answer is 32.187. Plus or minus 32.187 over 0.436. So I need H to be positive. I'm going to take the positive. So 32.187 minus 9.8, divide that by 0.436, and I get 51.34 meters. That is my HC. Which is what I believe I got before. So I got 25 plus 28. I don't know. Yeah, something seems weird here. Yeah, something's not right. All right, well, I'm not going to spend much more time on this, other than to state that if we measure this to be 0, and maybe that's what I did wrong, then mg, this is 25, that's the only energy there. This is 0 energy. And the energy down here is mg H final plus K H final squared over 2. Setting those two things equal to each other. Maybe that's what I did wrong. So M was 70 times 9.8. So 70 times 9.8 times 25, 17,150. Yeah. 70 times 25 is 17,150 is equal to 686 H final plus K was like 48. 48, 24. So my A is 24, my B is 686, and my C is minus 17. Minus 686 plus or minus. By this whole thing, so it's minus 686 plus or minus 254.99 over 2 times A over 48, and I'm going to go with, I need a negative, so 1455 plus 686 divided by 48 is 44.60. Yeah, I don't know. What they've got here is they have the initial kinetic energy. If you look, and I'm probably just screwed up because it's late, but the initial kinetic energy at Y1, V initial 0, V2 is 0. Now, what we need to figure out is, so the height at Y naught is Y1 minus L, where Y1 is 110 minus L, which is 25. So this is 85, the height there. X is 0 there. The X of the spring. And then when it gets down to here, the stretch of the spring is that distance. So maybe I'm just messing it up because I'm not being thorough enough. So if you compare this, or this energy to this energy, I guess is what they're doing. They're comparing 2 and 1. All right, they're just comparing 2 and 1. So MGY1, well, Y1 is 110, and MGY2, which we don't know, and 1/2 K Y2 minus Y0 is another way to do it. And then doing that, they're saying that you get this quadratic, and out of that quadratic, you should get 40. So follow their lead. I'm probably just doing something stupid with my math. You know, I'm just doing something. Anyway, all right, fine. That is that homework. I want to go to the chapter 11 one now. If I have some time, I might do the chapter 4. As I said, tomorrow we'll talk about the tests. I haven't graded except for like 30 of them that have 1 page to grade, so I've got an hour grade to do. One of them. All right, so onward to momentum and impulse. In this first one, 150-gram ball and a 250-gram ball are held at rest with a spring between them. When released, the lighter ball shoots away. Now, we have 2 balls with a spring between them, and they're being held there. So their momentum initially is 0. Their final momentum is M1, V1, and M2, V2. Spring just stays here, we assume. And P final, by conservation of energy or momentum, needs to be equal to 0 as well. Therefore, 0 has to equal M1 V1 plus M2 V2. Or V2, if I move it over, is equal to negative M1 V1 over M2. All right. So M1 is 1 point or 150, grams, divide that by 250 grams, and then multiply that by 6, and I get 3.6. Speed is magnitude, so it would be negative 3.6, but it's fine. So this is how we're going to do most of these problems when energy is conserved. Initially, the energy, or when momentum is conserved. Initially, the momentum conserved. Afterwards, the momentum still has to be conserved. Or initially, the momentum 0. So because momentum is conserved, afterwards, the momentum still has to be 0, and therefore we can quite easily figure out what V2 is. One down. A bird is flying along and it grabs a 15-gram insect with a speed of 35. Now, what is the bird's speed immediately after swallowing? Okay, so this is what is known as an inelastic collision. In all collisions, momentum is conserved. But the initial momentum is the mass of the bird, the velocity of the bird, plus the mass of the insect, the velocity of the insect. And then afterwards, the insect is in the bird's belly. So they have some V final. By dividing through by mass of the bird plus mass of the insect, I can find the final velocity. I have to be careful about the signs on my velocity. So it says a 250-gram bird, 50 grams, is flying at 6 meters per second, flies at an insect heading straight toward it at 35. Okay, 15 grams, and it's heading towards it. So the bird was going this way, and the insect was going this way. Okay, I'm going to choose this to be negative. So I'm going to choose that the bird is 250 grams and 6 meters per second, 15 grams and negative 35. I'm going to assume that the bird was positive and the insect was negative. So I get 250 times 6 minus 15 times 35 over 250 plus 15. I don't have to change my units. They're in grams and they'll cancel. So 250 times 6 minus 35 times 15 divided by 265 is 3.7 meters per second. That's quite a change, to be honest. That's a pretty big insect for a bird that size. Okay, so this is an inelastic collision as well as a bird. And conservation of momentum. A proton traveling to the right has a head-on elastic collision with a carbon atom that we're assuming is not moving. The mass of the carbon atom is 12 times the mass of the proton. So mass of carbon is 12 times mass of proton. And our proton is heading this way, and it hits this big old carbon. And the velocity of the proton was 2 times 10 to the 7th. Now, here we go. Elastic collisions. Momentum is conserved, kinetic energy is conserved. That's what makes it elastic. That means that we can use the following: V1 final and V2 final, assuming an elastic collision with mass 1 at rest or mass 2 at rest. We use M1 plus M2 minus M2 over M1 plus M2, V1 initial. And this is 2M1 over M1 plus M2, V1 initial. Now, in this case, we're asked for the proton. So mass 1 is the mass of the proton minus 12 MP. And this is over the mass of the proton plus 12 MP times 2 times 10 to the 7th. Now this is 1 minus 12 over 13. So this is negative 11 13ths, 2 times 10 to the 7th. That is 11 divided by 13 times 2 is 1.69 times 10 to the 7th with a negative sign. It hits this big old carbon atom and it gets knocked right back the way it came in an elastic collision. What is the speed of the carbon atom? 2 times the mass of the proton over the mass of the proton plus 12 times the mass of the proton times V1 initial, or 2 over 13. So 2 13ths times 2, 0.31 times 10 to the 7th, or 3.1 times 10 to the 6th. Okay. Whenever it's elastic, you know that the change of kinetic energy is 0, the change, and you use these two equations to find your final velocities. This is only if your second mass is at rest initially. All right. What is the direction of the proton after the collision? Well, it was traveling right, it's going to be heading left. What is the direction of the carbon atom? To the right. Okay, so they hit and they bounce off each other. Now it hits a stick. So ball clay traveling hits and sticks to a 1 kilogram brick sitting at rest on a frictionless surface. What is the speed of the brick? This is an inelastic. They stick. Okay. They stick together. So M1 and M1 V1 plus M2 V2 is M1 plus M2 V final. This is 0. The brick wasn't moving. 50 grams times 1 kilogram are 50 grams. Let's put that in kilograms. So 0.05, and it was moving at V naught. Okay. And so this is 0.050 plus 1.0 V final. And they ask us, what is the speed as a multiple of V naught? So V final is 0.050 over 1.050 times V naught, just divide by that side. So 0.05 divided by 1.05 is 0.05 or 0.047 V naught. They got 0.048. Okay, 0.048. I got 0.0476. 0.0476. All right. What percentage of energy is lost? This is the big thing. In an elastic collision, kinetic energy is not conserved. Okay, it's always less than 0, or usually, I think it could be 0, but it can never be positive. So the change in kinetic energy is the amount of energy lost. And that is mv final squared over 2 minus mv initial squared over 2. Sorry, I wrote that poorly. I chose poorly there. M1 plus M2 V final squared over 2 minus M1 V initial squared over 2. Now, we can rewrite this as the following. They want it as a percentage, so you can write it as the change of kinetic energy over the initial, which is kinetic energy final over kinetic energy initial minus 1, which is M1 plus M2 over 2. Let me do it on your page. Kinetic energy final over kinetic energy initial minus 1. That is the change of kinetic energy as a ratio over the initial kinetic energy. So this is M1 plus M2, 0.0476 V naught squared over 2 divided by m1 v naught squared over 2 minus 1. The v naughts go away, and what I get is I get m1 plus m2 over m1. The 2 cancel. The v naught squares cancel, times 0.0476 squared minus 1. M1 was 0.05, right? 0.05 and 1.0. So this is 0.05, 1.0, and 0.05. So 1.05 divided by 0.05 times 0.0476 times 0.0476 minus 1 is 0.9524. So 95% of, and I should actually probably say this, take the absolute value. This is a percentage. So this is 0.9524 times 100%. So about 95% of the energy is lost. It's a little weird, it's a weird problem, but what percentage of the mechanical energy is lost? How you do that is you take the change and divide it by the initial and multiply by 100%. Boom, boom. A small rocket. So remember rocket equations. And the rocket equations were that the thrust is minus Vx times the mass loss rate. Mass final is the initial mass minus R times T. And V final is V initial plus Vex ln mass initial over mass final. And this is also MA minus Vex over R. So we can find the acceleration at any time. So A prime is minus Vex R over M final prime. So we're told a 5 kilonewton thrust. So our thrust is 15, was it 15? 15,000 newtons and 300 kilograms of fuel in 30 seconds. So R is the change of mass over the change of time, and it's constant. 300 kilograms over 30 seconds is 10 kilograms a second. So R is 10 kilograms per second. All right. What is the exhaust speed? So Vex is, and we assume that the thrust is negative, so thrust over R, which is 15,000 divided by 10 or 1,500 meters per second. Okay, just rewrite that. Assume the thrust is negative. Was that really it? Oh, all right. Yes, that was it. So this is a little bit harder. What is, if the exhaust gas is 200 or 2,000 meters per second? So V exhaust is 2,000 meters per second. And mass initial is 5 times mass final. Once half the fuel has been burned, the mass of the fuel is 5 times the mass of the empty rocket. So actually, I shouldn't say that. What I should say is, following, I didn't read that very carefully. So the mass of the fuel is 5 times mass naught. And the mass of the rocket is mass naught. So the initial mass is 6, is the initial, let's call it. And then when half the fuel is burned, M final is going to be 3.5 mass naught, because half the fuel would be 2.5 mass naught, and this would be mass naught. The rocket, so 3.5. All right, so mass initial will be 6 m naught, and mass final will be 3.5 m naught. V final is V initial plus Vex ln mass initial over mass final. This is 0, this is 2000. So we have 2000 times ln, mass initial was 6 m naught, mass final is 3.5 m naught, or 2000 ln of 6 divided by 3.5. 2000 times ln 6 divided by 3.5 is 1007. So it's a 1080, 1100. Rounding up to 1100. Okay. All right. You all just believed when dinosaurs went extinct when it hit it. Suppose an asteroid with a diameter of 2 kilometers and a mass of blah, blah, blah hits the Earth with an impact speed. What is the recoil speed? So we are going to assume this is an elastic collision. The asteroid comes flying in and hits the Earth and impacts it. So m of the asteroid, v of the asteroid initial is m asteroid plus m Earth, v final, and that's the recoil speed of the asteroid, or I mean of the Earth. So v final is ma over ma plus m Earth, v asteroid initial. So the asteroid's mass really doesn't matter compared to the Earth. But its impact speed was 42 times 10. So this we can write as 0.6 times 10 to the 13th over, what did they go to 5.9? They just went with 6 times 10 to the 24th. Incidentally, this is 6 times 10 to the 12th, right? Times 4.2 times 10 to the 4th. Now, 6 divided by that is 10 to the minus 12 times 4.2 times 10 to the 4th. You add these when you multiply them, so I get 4.2 times 10 to the minus 8 meters per second. Very small. It's just in elastic collision, they stick together. Very small amount of recoil. Now, what percentage of this is this of the Earth's speed around the sun? Okay, so the Earth orbits the sun at a distance of 1.5, blah, blah, blah. Now, we need to figure out how fast does the Earth go around the sun. V is 2 pi r over t. R is 1.5 times 10 to the 11th. It was given. That is an AU. T is pi times 10 to the 7 seconds. You can figure that out. 365 days times 24 hours times 60 minutes an hour times 60 seconds. You end up with around pi times 10 to the 7. So the velocity of the Earth is 2 times pi times 1.5 times 10 raised to the 11th divided by pi times 10 raised to the 7th, and you get about 3 times 10 to the 4th meters per second, or 2 pi times 1.5 times 10 to the 11th over pi times 10 to the 7th. Pi's cancel. 10 to the 11th over 10 to the 7th is 10 to the 4th, 2 times. The Earth travels about 30,000 meters per second. Now, we got 4.2 times 10 to the 8th. So 4.2 times 10 to the minus 8 meters per second. 0.000000042 divided by 30,000 is 1.4 times 10 to the minus 12. As a percentage, that's very small. 1.4 times 10 to the 10th, because you multiply this by 100%. It's a very small change in the speed of the Earth. Okay. Stoplight has entered, heading north. When it's struck by an eastbound Volkswagen, they stick together and the skid marks are 35 degrees. So Cadillac's heading north, 2,000 kilograms, and its speed was 3.2. And 800 kilogram sticks together. 800 kilograms. And we assume that they hit center to center. We don't know what the velocity is, but we know that they stick together and they end up at 35 degrees as they skid to a stop. Okay. So what we have to do here is P in the X and P in the Y. Initial is P final, and that is M of, let's call this 1, and we'll call this guy 2. We'll call this 3. So M1 V1 X plus M2 V2 X is equal to M1 plus M2 V X final. And M1 V1 Y plus M2 V2 Y is M1 plus M2 V2 Y final. Y. Now, the Volkswagen was going in the X, and the Cadillac were going in the Y. So we get that V2 final is M1 over M1 plus M2 V1, VY final is V1Y, and the X final is M2 over M1 plus M2 V2X. Okay. Now, those two things end up being 35 degrees. So tan of the angle is V1Y over V2X. And we know that that has to be 35 degrees. We know what V2X is. We can find it. Okay, we can find it from this equation right here. So, I'm sorry, we know what, I did that stupid, sorry. Vy final over Vx final. So we can find what Vx final is. M2 was 800, M1 was 2000 plus 800 times V2X, which is 3.2, is Vx final. And so that is 800 divided by 2800 times 3.2. So this is 0.914 meters per second. And so Vy final is Vx final tan theta. Now, Vy final was M. Oh, shoot, I did that backwards. Sorry, guys. This is Vy. See, I'm confusing myself. All right. This is true, and that's tan of 35. This was Vx final because 2 is in the X. And 2000 over 2800 times 3.2, that's what I did wrong. I don't know what this is. This is unknown. This is what I want to find. And this was Vx final. This is Vy final. So Vy final is 2000 divided by 2800 2000 divided by 2800 times 3.2 is 2.2857 meters per second. So Vy final is 2.2857, 2.2857 meters per second. Vx final is Vy final divided by tan theta. And finally, M of the Volkswagen times V of the Volkswagen is equal to M of the Volkswagen plus M of Cadillac times V final, Vx final. So I want to solve for this. V of the Volkswagen is M of the Volkswagen plus M of the Caddy over M of the Volkswagen times Vx final. Now Vx final is 2.2857 divided by tan of 35. So 2.2857 divided by tan of 35 is 3.2643. And this is 2800 divided by 800 times 3.2643. So 2800 divided by 800 times that answer is 11.425. So the initial Volkswagen was 11.425 or 11.4 meters per second. Weird 11, I guess. So just to clarify what I did, we break it up into the X and the Y. The Cadillac was traveling in the Y. I keep wanting to do that. I don't know. The Volkswagen was traveling in the X, and then it ended up shooting off at 35 degrees together, both of them. So B plus C. The Cadillac was traveling in the Y, and we know the Cadillac was doing 3.2 meters per second, and it's 2,000 kilograms. The Volkswagen was 800 kilograms. Now, because it is a elastic collision in the X, M1 V1X, or M of the Volkswagen initially in the X plus M of the Cadillac initially in the X is equal to M of the Volkswagen plus M of the Cadillac V X final. In the Y, MV, V of the Volkswagen, the Y initial plus M of the Cadillac, V of the Cadillac. In the Y is MV plus MC, V final in the Y. Now we know that this angle is equal to V final Y over V final X. So solving these, because there is no X for the Cadillac and there's no Y for the Volkswagen, we get that Vx initial, which is the Volkswagen, is M of the Volkswagen plus MC over M of the Volkswagen times Vx final, and Vy initial of the Cadillac times M of the Cadillac. Let me just do it this way. V final in the Y is M of the Cadillac over M of the Cadillac plus M of the Volkswagen times V initial of the Cadillac in the Y. Okay, we know what these are. This is 2000, this is 2000 plus 800. This was 3.2. So we can find Vy final. From this, V final of X is V final of Y over tan theta. So from this, we can find Vx final. We know that this is 800 plus 2000 over 800 times V final of Y over tan theta. So whatever this is V final of Y divided by tan theta. multiply it by 2800 over 800, and you have the initial of the Volkswagen. It's kind of a cool problem to do since you have to do X and Y. All right. So this one is another of our collisions. 100-gram ball moving to the right collides head on with a ball that is moving to the left. They are both moving. Okay. If it's perfectly elastic, what are the speeds of each ball after the collision? So M1 V1 plus M2 V2 is equal to M1 V1 final plus M2 V2 final. Initial. Now, we don't have enough information right now. Okay. We have no idea right now of what these possibly are. However, we do know that M1 is moving to the right at 4 meters per second. And M2 is moving to the left at 3 meters per second. So let's try this instead. We do have V1 final and V2 final is equal to M1 plus M2. Keep doing that. Over M1 plus M2, V1 initial, and 2M1 over M1 plus M2, V1 initial. But these only work if this guy's initially at rest. Well, if this is initially at rest, okay, it would be the same as if this was moving at 7 meters per second and this guy was moving at 0. Let's try that and see what happens. So in the frame, that the whole frame is moving 3 meters per second, we're going to need to take that off. All right, so this would be, and M1 is 100 and M2 is 200. So 100 minus 200 over 100 plus 200, that is times 7. So this is 100 negative 1/3, negative 7/3. And this one is 2 times 100 over 100 plus 200 times V1 initial, which is 7. So that is 2/3 times 7. Okay, so negative 1/3 and negative 2/3. So we get 7/3, negative 233, 3, and we get 14 divided by 3, 4.66. Okay. I believe, so now we need to subtract, so this would be negative 5.33 and 1.66. All right. V1 is 5.33, negative 5.33. Okay, because I had to subtract 3 from it to put it back in there. And this one is going to be 1.67. You have to put it back. Now, why am I doing that? And remembering to put it back, because otherwise we have to use M1 V1 initial squared over 2 plus M2 V2 initial squared over 2 is equal to M1 V1 final squared over 2 plus M2 V2 final squared over 2. Solve this for one of them, plug it in to eliminate it, and do a whole bunch of algebra. We don't need to. We can actually, no, stop it. We can actually find a frame where this guy is at rest. How do we do that? We assume that the frame is moving that way, which means, or actually, yeah, we can assume that the frame is moving this guy's rest frame is moving at 3 that way, which means this one in the rest frame of 2 looks like it's moving at 7. Do the whole analysis the way we do it with one of them at rest, and then subtract the 3 afterwards, subtract 3 from each of them to put it back in their frame. Okay. All right. So what is the direction of the first ball after the collision? It's moving the opposite way. So it's moving to the left because it's negative. What is the direction? To the right. If the collision was inelastic, what is the speed of the combined balls afterwards? The nice thing is, inelastic, we don't have to worry about that. M1v1 plus M2v2 is M1 plus M2 v final. This was 100, this was 200. 3 to the left and 4 to the right, 4 and -3. So I get 400 minus 600 is equal to 300 times V final. So -200 over 300 V final. Yep. So V final is negative 0.66 meters per second. So they were moving this way, 2 was moving this way, and after they stick together, they're both moving that way at 0.66. What is the speed after the collision? In what direction? To the left. Okay. That one's not too bad. A neutron has a mass slightly greater than a proton. Free neutrons, radioactive decays. In one experiment, neutron decayed into a proton and electron. They were shot out back to back. The proton had a speed and the electron had a speed, and no other decay particles were detected. Okay, so before it decayed, the neutron was just sitting there. And then it decays into a proton and an electron. The proton has a mass of 1.67 times 10 to the minus 27. The electron has a mass of 9.11 times 10 to the minus 31. Okay. And the proton was 6 times 10 to the 5th. I'm going to call that negative. The electron was 1 times 10 to the 7th. And it was positive. So if we add these two momentums together, we should get 0. So I get 1.67 times with a negative 6 times 10 to the minus 27 times 10 to the 5th. And I get about 10 times 10 to the negative 22, adding these things together. Here I get 9.11 times 1 times 10 to the minus 31 times 10 to the 7th. I get about 10 to the 24th. So no, it does not. There's a factor of about 1 times 10, whatever, 10 to the 20, 100 times 10 to the 24th off. The neutrino was emitted in the above, in what direction did it travel? So if there was a neutrino, it would have had to go in that direction with an energy or a momentum of 100 times 10 to the minus 24, so that this would add to that and we would get, or 90, let's say. 900 times 10 to the 24, 890, 990 times 10 to the negative 24. I can't do that. In the same direction as the electron, because the electron has less momentum than the proton. Okay. How much momentum did the neutrino carry away? 9.9 times 10 to the minus 24, or 990 times 10 to the minus 24, or 9.9 times 10 to the minus 22. Okay. Alrighty, and that's it for momentum. Our last set that I'm going to kind of go through a little bit fast, and I'll do something later. These quick 5 I'll talk about really fast, and at least you can see. Now, the deepest point is 11 kilometers below sea level, deeper than Mount Everest is tall. What pressure is the atmosphere? So, P initial plus rho G H initial plus rho V initial squared is equal to P final. This is Bernoulli's equation. But if we assume that the particles aren't moving, we get this, assuming this is sea level. Our density is water, so it's 1,000 kilograms per meter cubed. Our initial pressure is 1 atmosphere, 101.35. Hang on one second. That's right. No, chapter 14 won't be on it. Our final pressure is what we want. That is P initial plus rho G H initial minus H final. H initial is 0. H final is what, 11 kilometers, 11,000. So what we get is 101.325. I think I have that backwards. Oh, no, I don't. This is a minus 11 kilometers below. So it's a minus minus. Plus 1,000 for the density of water, 9.8, 11,000. So 101.325 plus 1,000 times 9.8 times 11,000 is 1, 2, 3, 4, 5, 6, 7, 8, 1.08 times 10 to the 8th pascals. Which if we divide by 101.325, we get 1064 or 11,000 atmospheres. So really fast, 1 atmosphere at the surface of the Earth is 101.325 pascals. That's also 14.7 psi. That's also 760 torr, or otherwise known as millimeters of mercury, if they give it to any of this. So the next one, tall cylinder floats in mercury. The axis of the cylinder is perpendicular. What length of steel is above the surface? Buoyancy. Okay. What this means is for something to be buoyant, then the force of buoyancy minus the weight has to be equal to 0. But density is mass over volume. So what we're going to do is, and this is the buoyant force, is the mass of water displaced times G. So what we get here is, this is the density times the volume inside, which is volume in, times G minus the density, the volume total, G is equal to 0. Now the volume total, V total, is A times the whole height, and V inside is A times little h, the amount floating in the surface. We move this over, what we get is V in, and this is of the water, and this is of the object. So we get the density of the water or fluid, V in, is equal to the density of the object, V total, or the A's cancel, and what we get is density of water times H is density of the object times little h. Did I do that backwards? Yeah, I did that backwards. So I'm trying to go fast because I have other stuff to do now. H, big H. Now, where did that go? So we're told the density of steel, we know the density of water, we know the diameter, we don't care about that. The axis is perpendicular, so what length of steel is above the surface? Okay, so what we want is we need to find H, and little h is equal to density of the object over the density of water times big H, and then take H minus H, okay? So H minus H is H minus rho over rho omega is H, and that's how much is in there, but regardless, let's just find little h. So little h is the density of the object, which is 79,000 divided by the density of the water. No, I have that backwards. So this is blah, blah, blah. I have that backwards. All right. H, and the whole thing is H. The buoyant force minus the weight is equal to 0 because it's not going anywhere. And the weight is the density of the object times the area times the height of the object times G. The density of the water times the area times the height times G. So density of the water times H is equal to density of the object, which is G. And that doesn't seem right. Seems like it's supposed to be flipped. Yeah, I do not get what's going on there. So oh, see, I'm dumb. It floats in mercury, okay? And mercury has, yeah, I was right before. Sitting there looking at this and I'm like, man, that means that the height is going to be the density of the object over the density of water times H, and this would have been 79,000 over 1,000, which would have meant a greater than the height is out. It wouldn't have made any sense. But this is mercury. Mercury is 13,600. So 13,600, and the height of the entire cylinder was 70. So 7,900 divided by 13,600 times 0.70, or let's just leave it in centimeters. No, 7,900 divided by 13,600 times 70 is 40.7. So this is 40.7. This is 70 centimeters. And 70 minus 40.7 is how much is above the water. 70 minus our answer is 29.3 centimeters. Okay, that's how much is above the water. All right, or above the mercury. Now in this one, Pascal's principle says that the pressure in is equal to the pressure out, but that means force over area is equal to force over area pressure. So on a hydraulic lift, a 75 kilogram times G, and this is a 1,400 kilogram, and we're assuming that the lifts have a diameter The piston is round, therefore it is pi r squared or pi over 4 d squared, because d is r to the half. R is d to the half, I should say. So what we get is we get 75 times 9.8 over pi to the 4th times d in squared is equal to 1400 times 9.8 times pi over 4 times d out squared. The 9.8s go away, the pi to the 4th, and what we get is 75 over d in squared is equal to 1400 over d out squared. This is 2, so what is the diameter here? This is 2. di is 75 times d out over 1400. And d out is 2. So 75 times 4 divided by 1400, square root of that answer is 0.46 meters. The second student joins the first. The height difference between the left and right is 40 centimeters. What is the second student's mass? Okay, so now the work. So the work has to be the same. So mgh has to equal mgh. And this was 1400 times 9 point. No, I did that wrong. So hold on. We know that this was mass 1g, and this is mass of the elephant g, and it went up that height. So that amount, right. Force 1 times h has to be force 2 times h. And I know I'm doing that wrong. So, right. So it is pressure minus rho gh is equal to pressure out in, pressure out, and pressure out was the force of the elephant over the area on elephant. This is the height. This is the force of the students over area of the students. And this is 1000 times 9.8 times whatever the height change was. 30 centimeters, so 0.4. Oh, this is times that mass. This is mass of the elephant times g. This is pi to the 4th times b that the elephant's on. So we get mass 1 plus mass 2. These are the masses of students times g over d of the student squared, pi to the 4th. Plus or minus, I guess, is equal to the mass of the elephant, g over pi to the 4th, d of the elephant squared, plus rho of water, gh. And this was 1000, 9.8, 1.4. When you solve this, you get 61. Solve it, it's late. I have 2 minutes left. I'm gonna get out of here. Vertical pipe falls straight down into a bucket. The water exits the pipe at a speed of 2 now. It leaves here and it travels down to here. Pressure. Rho gh, rho gh. Rho v squared over 2 plus rho v squared over 2. It's outside, so the pressures are the same. The heights will be different, but I can get rid of all of these. I get gh plus v, gh1 is equal to gh2 plus v2 squared over 2. Multiply through by 2. I have one last thing I have to do here. Now, what did I want to know? Vertical pipe emerges 16 centimeter diameter cylinder and falls straight down. So this is 7.5 meters. This is 0. This is 2.0 squared. This is 2, 9.8. This is 2 times 9.8 times 0, and this is unknown. So V squared, or V2, is 4 plus 2 times 9.8 times 7.5. Okay. So 4 plus 2 times 9.8 times 7.5. Square root of that answer is 12.3 meters per second. Okay. But we want to know the diameter of the column of water. So by the A1 V1 is equal to A2 V2. And we now know this was 2 and 12.3. If it's a circular column, then this is pi d squared over 4 and pi d squared over 4, 1 and 2. I want 2. Pi's and 4's go away, and I get that d2 is the square root of d1 squared over times 2 over 12.3. D1 was 16 centimeters, 0.16. So 2 times 0.16 times 0.16 divided by 12.3. Square root of that answer is 0.065 centimeters. 6.5 centimeters. Sorry, this is meters. So what this thing does is it comes out and it goes to about half the diameter. That's why water does that in your sink by the continuity equation. All right, and our final, let me make sure that there wasn't anything else on that. Okay. And then coronary artery diameter, blood pressure dropped by 3 millimeters of mercury over this distance. So one last thing. Now, P1 plus rho G H1 plus rho V1 squared over 2 is P2 plus rho G H2 plus rho V2 squared over 2. Now, 30 centimeter long left coronary artery is 4.6. So A1 V1 is equal to A2 V2, and A1 is pi the fourth times 4.66, so 0.0046 squared. So diameter of top one. I don't know what this one will be. Delta P is 3 torr. Okay. And remember that there are 101, 325, 101, 325 pascals per 76 torr. So if I multiply that, that is 3 divided by 760 times 101, 325 is about 400 pascals. Okay, so the change of pressure, which is P2 minus P1, is about 400 pascals. All right. So they want to know, what is the average blood speed through the artery? So this is through the artery. So I have rho V2 squared over 2 is equal to rho G H1 minus H2 plus rho, let me rewrite this the following way. Do I know So, oh, I don't need that. So, okay. So the, I'm trying to remember. Um, hmm. I'll come back to this. I'm out of time anyway. I'll show you how to do this later. My brain's shut down. Anyway, I'll see you guys tomorrow. I'm gonna finish grading the last of the last page that I have of, like I said, like 30 tests. And we'll talk about the test tomorrow. See what we want to do with them.
Thank you, Professor. Have a good night.
You two guys. This will be posting in, I don't know, an hour maybe. But I'll see you.